So in the last class, we've looked at the simplest DC to AC converter. In the context of the converter, we talked about what we call as the voltage source inverter, where the source is a voltage stiff element and the load is typically a current stiff element. And we'll not look at the current source inverter idea, but the idea of it will be simple, this kind of thing, where you have a source which is current and the load which will be voltage stiff, whatever is the load. So typically they'll have a capacitor arrangement to make it voltage stiff at the load side. And whatever we had, you can have a thyristor based current source inverter, or we could have had a transistor and a diode in series, transistor IGBT in series with this one. So this is a current source inverter. We have looked at that. Now the simplest, the minimum requirement, we said that it is average voltage of the AC should be 0, and we would like to have a symmetry for the waveform, the output voltage waveform. And the simplest solution for that, we found that it is a square wave. If you do the square wave for the half bridge inverter, where you have the load connected to a reference point, which is exactly in the midpoint of your or O point of your inverter, and you will have only one SPDT switch. Okay, one SPDT switch realization. So this pair of switches would realize an SPDT operation, and we'll get what we get would be, we'll keep the S1 on for 50% of the time and S2 on for the second half of the time. And with respect to the O point, this is V, let me call this point as A. It'll be VAO. If you plot it, it'll look like this: plus VDC by 2 and minus VDC by 2 with respect to the midpoint, the center point, the O point. Okay. So the duty ratio here is 50%. And we have exactly 2 switchings per cycle. Okay. So you have one switching, upward switching here, and one downward switching here. This becomes the next switching. This switching is exactly corresponding to the next cycle, the new cycle. So you have 2 switchings per cycle. Per cycle. Okay. Okay. So for a 50 hertz waveform, you will your inverter will be switching at 100 hertz. The number of switching happen in a the total number of switching happen in the inverter will be 100. But we'll define the switching frequency corresponding to this as 50, because together this upward and downward together we call it as the inverter switching frequency. Anyway, and we also said that based on the Fourier analysis, we can say that the fundamental voltage, which would be a sinusoid, it will be exactly the peak value of the square wave multiplied by 4 by pi. And in this case, peak value is VDC by 2, and therefore the maximum fundamental voltage which I can obtain, or the fundamental voltage which I can obtain from this one, is 2 VDC by pi. Now the only way to control the output fundamental, if you want to change it, will be to change the VDC. All the others are constant, and we have a you need to have a rectifier or a DC to DC converter at the front end if you want to change the output voltage for a given VDC. Okay, so you have to change the VDC itself to get the output voltage VO. Now, if it is a full bridge inverter, what we call as the H bridge inverter, then we have 2 legs. Okay, so this is leg A and this is leg B. Okay, I think I have named it the other way around. Let me use leg B. Let me name this as leg A. And because my voltage is defined as this one, so this is point A, node B, and we have VAB, which is a floating voltage. There is no fixed this one. because the point A as well as point B can be connected to the plus VDC or minus VDC. So the leg voltage here is VA, and perhaps with respect to some, let's say, neutral point, or you could have had a imaginary O point also, whichever it is, but some reference point which is fixed. So A with respect to O can be defined here. B with respect to O can be defined here. So VAB is essentially VA minus VB, VAO minus VBO, or VAN minus VBN, whichever it is. But the point here is that VAB is a floating voltage because neither point A nor point B has a fixed potential. It keeps changing. But the output is going to be plus VDC, because I can have VAO as, if you remember your half bridge, from the half bridge analysis, VAO with respect to the imaginary center point here is going to be VDC by 2, and VBO is going to be VDC by 2 or 0, or here it is going to be 0 and VDC by 2. Sorry, it's not 0, minus VDC by 2, and here it's going to be plus VDC by 2 minus VDC by 2. Now the combination could be anything, and we can get, suppose if I choose this as S1, S2, S3 and S4, then I choose S1 and S4, I get plus VDC. I use S3 and S2, I get minus VDC across the load, and therefore I get the plus VDC minus VDC in total. And of course, the fundamental voltage of that would be 4 by pi times VDC. Okay, so that will give me the peak value of the fundamental from the Fourier analysis, and then we can get sin omega t, which will be the, because it's a sinusoid. So this is a fundamental voltage which I can obtain across the load. And as we already discussed in an earlier discussion, that the fundamental voltage would be the major contributor to the work done, because mostly the voltage harmonic and current harmonic, unless they are having the same frequency, they will not produce any useful power. If they have voltage as well as current has the same harmonic, then it will produce the power. However, many a times that power produced could be a heating power rather than useful power. The work done would be it's like a lost energy rather than this one. So the fundamental is the major contributor to the your work done, and therefore we are interested in the fundamental. Now we would like to control the fundamental, as we already mentioned. You can always do that by changing this, or if that, but this VDC variable implies that you need a front-end converter, front-end rectifier, or a DC to DC converter. And that gives me, I mean, that again is a controlled converter requirement. But instead, we can actually utilize our own switching strategy and perhaps control the voltage. So how can we do that? Now, as I've already discussed in the previous HBRID discussion, we have bipolar options also, in the sense that in the previous example which we started, we said that I will keep this S1 and S4 on, and S3 and S2 on, right? These are the combinations which we had. But we can always have S1 and S3 on, which would mean that you will have zero voltage across the load, because if I keep S1 and S3 on, both will be connected to the positive DC link rail. Whereas if I connect S2 and S3, S4 and S2, I'm sorry, it'll be, the load would be connected, the load would be shorted across through the negative DC link rail. Okay, so 3 and S1 load shorted through the positive DC link rail. Okay, and similarly S2 and S4, everything, only thing is that it will be negative DC rail. Okay, so this is the arrangement. So by doing that, I should be able to generate some 0 voltage for a shorter while, and that's precisely we are going to use it. So the strategy which they use is what we call as voltage cancellation method. So what they do, like we have VAO, which with respect to I have used N here. Anyway, so this is O point or N point, whatever it is. So VAO is like this. It is either with respect to O point, it could be either 0 when it is connected to this one, or when it's connected to the top point, it will be plus VDC, right? So it will be plus VDC or 0. So if you shift it to the center point, it would have been plus VDC by 2 minus VDC by 2. It doesn't matter. But it's some common reference point. Now I have chosen the negative of the DC link as the reference point. So it's plus VDC by 2 minus VDC by 2. With respect to the center point, which is imaginary in this case, we don't have a center point here. Or we can have 0 and VDC. Anyway, so we have VAO, which is between that, VBO, which is again 0 and VDC. Now what we can do is that if I keep this on for 50% and keep this on for the remaining 50%, I would get exactly the square wave which we have already. That's what we've done, right? It will be S1 and S4 be on, turn it on for this one, and sorry, this is S1, this is VBO, should be corresponding to S4, and here it is S2, and here it is S3. Okay, so this is the arrangement. So which means that it is S1 and S4 here, S2 and S3 here, and we get the voltage like a square wave. Now if I shift, I start the switching of S3 a little earlier. So that's what we did. So from the original thing, we have shifted it a little towards the left. This is what I done. So what would happen? There is an instance, there is a region which is going to be getting cancelled by the two of this thing. So here again, we have plus VD. This is also plus VDC here. And here again, it's plus VDC. Those gets cancelled. In the VAB, which is VAO minus VBO, we have that cancel. Here it is plus VDC, here it is 0. In this region, it is plus VDC and 0. So we get plus VDC here. In this region, it's plus VDC minus plus VDC. I get 0 here. In this region again, this is 0 minus plus VDC. That will be minus VDC. Here again, 0 minus 0, because this is nothing here. It's already shifted over there. So 0 minus 0, I get 0 here. Okay. So again, it is plus VDC. It is, let me write it here, plus 0, it will be plus, 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 it will be 0, and 0 plus it will be minus. Here it is 0, 0, it is 0. Again, it is plus 0, this plus. So it will go on like that. So the more the overlap we give, that is this angle beta, which is what we call as the overlap angle. So overlap angle beta, if you keep on increasing, that is, there is more and more part of the VBO which will coincide with VAO, the more the cancellation would be. And we get that if you have this kind of an arrangement, the beta can vary from 0 to 180. So if I shift VBO all the way to the left side, shift by 180 degree, so what would happen? The entire voltage waveform would be cancelled. VAO minus VBO would be 0 all the time if you keep shifting it all the way to the left side, VBO. So if you move it all the way here in this side, it will give me 0 voltage. If you move all the way to location 0, that is beta is equal to 0, then it will be exactly the maximum voltage. So the maximum is 4 by pi VDC, and as we move, we get that the voltage is reducing. So when beta is equal to 0, I should be getting the maximum voltage. When beta is equal to 180, I should get 0. So it will be cos of pi by 2. That will give me the minimum voltage. So this is the expression which we get. VO1, that is VO fundamental peak value, would be 4 by pi VDC cos of beta by 2. So you can verify that by calculation also. But I just wanted to give you intuitive thing. When beta is equal to 180, you get 0 here, because cos beta by 2 is cos pi by 2, which is 0. Whereas beta is equal to 0, I get the maximum voltage. So the overlap would take care of the control of the voltage. This is a very simple idea, but very effective. Now, the other idea to control the fundamental is to have a pulse width modulated operation. So here, the downside of this particular arrangement is that it does the voltage cancellation. It really does the voltage cancellation and thereby controlling the output voltage. So VO1 is controllable. Okay. Now the only thing is the control is not linear. That is one thing. The second thing is that I don't have any control over the harmonics which is generated by this one. So if you remember, a square wave had all the harmonics starting from the fundamental. You can always remember that it's a half-wave symmetric, quarter-wave symmetric waveform. So it turns out that it will only have the sinusoids and only the odd number of harmonics. Okay, so if I plot the harmonics and the magnitude, it turns out that it will be something like this. It will be an exponentially decaying curve of the harmonics, but only existing at the odd harmonic. Okay, so this is what we get. So remembering that, we know that a square wave will have huge amount of harmonic. In this case, when we are doing the voltage cancellation, we are definitely getting a quasi square wave operation. We may reduce some harmonics, but not by our control. It just so happens. But at times, the entire voltage cancellation would mean that you will have only, you will have harmonics which may be dominant than the fundamental. So we don't have any control of the harmonic, and that is one thing which we have. So people have come up with the idea of pulse width modulation. So the PWM control of single phase H bridge, this thing, if you consider what they do, the simplest idea, there are multiple ways of doing the pulse width modulation. One of them is what we call as the sign comparison PWM, or just sign triangle PWM, sometimes they call it, or just sign PWM. Okay, in this case, we are considering the bipolar PWM. So what they do is that you take a carrier, which is a triangle, or it could have been a ramp also, in the sense that it would be a sawtooth waveform or a triangle. Now the side effect of a sawtooth is that whenever you have this downslope, it is very quick, and that will essentially cause additional switching. So traditionally, the triangle waveform is preferred over the sawtooth, because there's no compulsory switching because of this fast downgoing slope of the sawtooth. Okay, so I'm sorry. we have two things. One is a modulating wave, which is a sinusoid in this case. We call it as V control. If you recall the H bridge with DC to DC conversion, we use the same notation, V control. And we have a V triangle, which is the carrier wave for us. Now, what we have to do is that we need to compare which is larger at what point. The logic here is that whenever V control is greater than or equal to V triangle, we say that it is a logic 1. Okay, so we'll choose the VAB to be the plus VDC by 2 in this case. I'm sorry, plus VDC in this case. And whenever this is other way around, V control is less than V triangle, we choose minus VDC. All right, let's look at the situation here. In this region, let me highlight it. In this region, I see that the triangle is smaller than the side, and therefore VAB is plus VDC. In the other region, the triangle is larger than the sinusoid, and therefore we choose it to be negative. And in this region, again, this entire region here, the triangle is smaller. And again, this region, entire region, the triangle is smaller. This region, the triangle is smaller, and so on and so forth. Whenever the sine is greater than the triangle, we get a positive output voltage. And whenever the triangle is larger, we get a negative slope, okay, negative going part. This is corresponding to the triangle greater than sine. Okay, so by doing this, if you look at this TC period, so what would happen in every TC by 2, which we are going to call as the TS period. Okay, so every TS period here, if you look at the volt second, okay, if you choose the triangle frequency, it will be much higher. So what would happen is that it is like you have a triangle which is running very fast, and the sine is as slow as a DC, very slow. Okay, suppose if your triangle is at 50, the sine is at 50 hertz, and the triangle is running as fast as 10 kilohertz or 20 kilohertz, your sine would be extremely slow, the variation, and therefore we can consider it as good as a DC. In the short time period TS, it is almost close to a DC situation. And we can show that the volt second here in this region, let me draw it. So if you look at the volt second here, I would have got some positive here in this region, and I would have had some negative in this region. Whatever is the resultant would have given me an equivalent voltage, which would have been, we see that this is the positive region is a little higher, negative region is a little lower. I would have got some non-zero pulse here in the first half cycle. In the next half cycle, again, you have similar thing. And now next TS period comes here. Okay, so this is a TS period. This is another TS period. And this together, it is a TC period. Okay, the triangle frequency or the carrier frequency is dependent on TC. And we call the sampling period as half of the triangle period. Okay, and we can actually get the volt second in half of the triangle period, even though it is not a repetitive thing, but the volt second balance happen every TS period. So we call this as the sampling frequency, that is 1 by TS, which we call as Fs, is the sampling frequency. And this TC would correspond to the inverter switching frequency. It is double of this one. Okay, in this case. Yeah. Now, as I've already mentioned, the control logic is V control is greater than V triangle. We'll have the upper switch on and lower switch off. This is the bipolar PWM. Bipolar sine PWM or SPWM. We get VO is equal to VDC and V control is less than V triangle. We'll have SA minus on and SB plus on. Then we get VO is equal to minus VDC. And we already found that VO1 would be, VO1 peak would be proportional to VDC, but by a scaling factor MA. Now, in this case, we already identify that the volt second is dependent on the pulse width D, and that D in turn is dependent on the V control voltage. The larger the V control is, the larger would be this one. D at every, this thing is proportional to V control, and MA will depend on the V control peak, because in a sine PWM, the peak value of the V control keeps increasing and then decreasing, and it go to 0, then it will go negative, right? So in this case, we would be interested to find out the modulation index based on the peak value of the sine. Okay, so V control sine, V control peak hat is V control peak, which is peak value of the sine or the modulating wave. V triangle peak is the peak of the triangle. Okay, so you have the triangle here, we have the sine going like this. The sine peak is V control peak, the triangle peak is the V triangle peak, and that gives me the modulation index. And we see that the VO1 peak, while the sine peak is always smaller than the triangle peak, we have a guarantee that the V control is proportional to D of every TS period, and we have that VO1, which will be MA times VDC, or MA times VDC times V control peak by VDC, V triangle peak. So this will be my VO1. So by controlling V control, the peak value of V control, I should be able to have any of the desired voltage, so long as I have the V control peak is smaller than the V triangle peak. We'll see that why it is important. So the good thing about this scheme is that it is very simple to implement, because it's just a comparison, and it being very simple, it can also be implemented on an analog fashion. You take a simple comparator and you give a sine here, and you give a triangle here. Use the comparator, analog comparator, you can always get a pulse here. Okay, and you can just negate the pulse, get the inversion of the logic, you should be getting the negative pulse. Okay, so it is not very difficult to generate just hold on for a moment. Okay, so it's not very difficult to generate a logic of this sort, and it is possible to do analog implementation and as well as digital implementation. So in the olden days, in 1970s, 80s, when the computer was not so popular, this was a very common method to generate the pulse width modulation. Right. So we call that MA as the modulation index, or rather, to be precise, it is amplitude modulation index. So that's why the suffix MA, A comes there, amplitude modulation. The modulation index of amplitude. Now, we look at the spectrum here of this particular waveform. Now, I have assumed that this Fs is sufficiently larger than f1. This is the assumption which I made. But in general, if you plot the modulus of the harmonics, only the magnitude of the harmonics, fundamental as well as harmonic, for h is equal to 1 to n. Okay, this h is equal to 1. And you have the fs, whatever the number it is. So we find that it'll have a component exactly at fs. We have one component, and we'll have one side lobe for that, which is fs minus 2f1, and then I have fs plus 2f1. Similarly, at the second harmonic, you will have 2fs, and here it will be 2fs minus 1, 2fs minus plus 1. Then you have here 2fs minus 3. In fact, 2fs minus f3f1. It should have been 2fs minus f1, 2fs plus f1. So this, again, here it will be 2fs minus 3f1. Let me write it a little clearer. 2fs minus 3f1, this one, and so on and so forth. So this will be plus 3f1. So you will note that this f1 is the fundamental frequency, fs is the switching frequency. We'll have various side lobes here. It's like this is one lobe, and this is one. This is one group of harmonic content. Okay. Now it is separated widely by this one. The more you choose the fs, the separation would be higher. Okay. So we would want that fs to be much larger than f1, so that all the harmonic voltage content would be shifted to the right side, and the filters can eliminate that harmonic part. So if you use a nice filter here, what would happen? I'll use a filter like this. It'll reduce, it'll give very low gain for the higher frequencies if you choose the filter appropriately. Okay. The filter action would ensure that only the fundamental would survive, or the harmonics would be significantly reduced. Now the harmonic content, it occurs this way, that fh would be some jmf plus k times f1. Okay, so we have chosen mf as the ratio of fundamental, the switching frequency to the fundamental, and fh in general would be some jmf plus k all times f1. And it so happened that if j is odd, then k will be even, and vice versa. We'll not get into the details of that thing, but just remember that here you can see that if fs is odd, this would be even. Here again, if this is 2fs, it is even, and therefore the side lobes which it exists for this one would be odd, corresponding to the odd frequency. Okay, so f1, 3f1, etc. So side lobe would be exactly like that, and this will be actually coming down. In fact, this shouldn't be like this. I should have drawn it small. Okay, it's like this only, the small one. So as the now 3fs, you will see that the peak is much smaller. Okay, so this is the nature of the harmonic content in the pulse width modulated sine PWM modulated waveforms. So we what is the constraint on MF? Whether we have to look at the ratio to be in a particular manner. So we assume that MF is an odd integer to avoid subharmonics. Why do we say so? Because if I have a waveform which is like this, and I have, let us say, some waveform which is like this. So what would happen? And let us say this is at 50 hertz, and the other is at 170 hertz, or let us say 270 hertz or something. So what would happen? There would be instances where you would get this zero crossing matching, and then subsequently it'll move away. So there is a very low frequency movement between the zero crossing of the triangle and the zero crossing of the sign. It'll coincide once, then it'll move away. It'll again come back to coincide again with the zero cross. So that there will be a very slow varying synchronization issue, which would result in what we call as a subharmonic in the one. So what it means is that when you take the spectrum, you would have had fundamental here, and there is a very slow varying component because of the mismatches. So this is fundamental, but this is a subharmonic in the sense that it is smaller than the fundamental. This is 50 hertz. You may have a 2 hertz variation or 1 hertz variation of the mismatch. So we would prefer to have this to be an odd integer. Okay, let me clear this. I would want this to be an odd integer if possible. That will always ensure that the zero crossings would always align. Okay, if it is a fundamental frequency of 50 hertz, if I choose it to be 2100 hertz or something, or 1800 hertz or something, which should be an some odd integer rather than this one. In fact, 1000, not 1800. It should be odd. Okay, if it is odd integer, I will always have, let us say, this zero crossings always match. If it's a sine, and if you have 5 times the frequency, I'll have 50% aligning with this one, then again 50% aligning with this one, and it will go on. Okay, so the zero crossing of this all would be matching every time the sign crosses zero. There are 2 instances in a full cycle. Both the time it should match, and that will give me a safe thing. So there is no subharmonic in this case. Now, for very high frequencies, or when MF is greater than 21, that is what is experimentally or empirically found out, that if you choose MF sufficiently large, then even asynchronous PWM may suffice, in the sense that I can choose, if it is a 50 hertz F1, I can easily choose 2500 hertz, which is essentially like 50 times. It's a even multiple, but it wouldn't matter. Even if it is 35 hertz, I could still use a 2500 hertz here. And the subharmonic, it will be there, but it is negligible or insignificant in these cases. So if MF is larger, sufficiently larger, at least 21 or above, then we need not keep the MF always an integer. Now this becomes particularly important if you have your F1 varying, which is a case if I have a motor kind of situation. So when in the motor motor control scenario, you might be having an induction motor. So induction motor, we know that the speed can be controlled by changing the fundamental frequency, preferably. So many a times, to keep the flux constant and the torque constant, we choose what we call as a V by F control. Okay, which means that if I have a 50 hertz waveform, if it is 230 volt and 50 hertz at the rated condition, if you want to operate at 5 hertz of the, or suppose it is corresponding to 1500 rpm or near 1500 rpm, and I use 50 hertz, and let me write it down. So if I have an induction motor with 1400 and 420 rpm at 230 volt 50 hertz, I might be getting some torque. Now, if I want to operate this at 140 rpm, then I would be applying 23 volt and 5 hertz, and that will give me the same torque, same flux and same torque. Otherwise, you might have lesser torque available to you. So this is what we call as a V by F control. This is the essence of V by F control, and it becomes a prominent issue if you have a V by F controlled inverter drive, then keeping the switching frequency at 2500 might be easier for me. So if I keep it for 50 hertz, which is the highest frequency, I designed that to be 2500, then any lower frequency, even though it is not integer multiple, it could be okay. If you want to keep it as with always integer multiple, then what would happen is that at 5 hertz, your this thing would be, let us say, 21 times. So 5 hertz into 21, you would be getting 105 or whatever. Okay, it'll be a smaller frequency, and at a higher frequency, higher this thing, 50 hertz, you will be getting 1050 or whatever that number. All those things would keep varying. So switching frequencies are not a constant. In this case, I can always keep it at 2500, and we don't have to worry about the subharmonic, because since MF is much larger than, that is, FS is much larger than F1, or MF is larger than 21, the amount of subharmonic generated by asynchronous operation is insignificant, and therefore we can operate it as asynchronous PWM. But for if M is less than this one, for example, if you want to keep it at 15, MF is equal to 15, or MF is equal to 19, or MF is equal to 9, etc. These are possible, but you have to keep it at exactly 9. So if it is operating at 5 hertz, 9 times 5 hertz. If it is operating at 50 hertz, it will be 9 times 50 hertz, so on and so forth. So you will keep varying the switching frequency in that case. So these are the two options: synchronous PWM and asynchronous PWM. Now, for synchronous PWM, as I said, we choose it to be odd integer, and we ensure that the zero crossing is matching for both the carrier and the modulating wave, the triangle and the sinusoid. Zero should match. Also, it should ensure that this is an upslope, upgoing slope. This is also an upgoing slope. And here, this is a down going slope. Here, this is also downgoing slope. So by choosing it to be odd, we ensure that this happens. This gives me the best harmonic performance. And in fact, it's not, you can verify if you want to do that. You can take a PWM like using a comparison of these two. Choose MF is equal to 9 and MF is equal to 10, and see if there is a difference in the harmonic behavior. It is always interesting to see that. So if you choose that to be integer, you get some harmonics eliminated. But if you choose it to be even integer, what would happen? Then at the zero crossing here at the midpoint, that's 180 degree point. If you have the zero crossing, the 180 degree zero crossing would be this pi zero crossing would be, the sense of that would be, it will be upslope instead of downslope of this one. So this would have been, the triangle would have been like this. The sine would go down, the triangle would go up, and that could result in slight amount of harmonic, more harmonic content than the odd integer. Anyway, so we max the zero crossings. We ensure that the slopes are also in the same direction, and that give us the best harmonic performance. Now, there is one more interesting concept here which I have to discuss today. So this is what we call as overmodulation. What happens if the peak value of V control peak is greater than the triangle peak, or this is the triangle peak which you see here, at least at certain region, that is from here to here, at least here to here, I have the V control peak. V control is greater than V triangle peak. So this is the peak of the V control. So, and in and around that you have this one. Okay, so there is a region over here where the triangle peak is smaller than the modulating wave peak, and in that region we lose the pulses. Okay, there is no pulse corresponding to this switching happening. Whatever this action, the carrier is moving back and forth, it doesn't generate any pulse. So what would happen there is that it is a fixed waveform, and I don't have any control over the fundamental in that region, or the volt second balance is not maintained or not guaranteed in this region, and that will result in some missed pulses, or we can't do anything better because we already given the full pulse, and but the modulating wave is asking for more. So what would happen in this region? There is no pulse. It will give you a slightly increased fundamental overall, because you are missing more and more pulses. You will get more and more fundamental, because it's square wave is the highest fundamental which you can ever get from an inverter. So if you choose anything pulse width, you are actually losing on the volt second, right? Because if it was a square wave, I would have got the maximum fundamental. The moment I choose and give a notch into this one, whenever I have a notch, it's like I chopped off some volt second from here. Again, I chopped off another set of volt second from here. So you're going to get lower and lower fundamental. But in this region, I don't have anything to do. It's already reached the full width. There is nothing to chop off. We can only, you would wish to have increased the magnitude of the volt second, but we don't have an option because it is the maximum VDC which we get. So this missed pulses, more and more pulses would start be missed. If you keep, let us say, we choose this to be larger like this, then I miss more and more pulses, because this is the only switching which will happen here, and here again is the next switching which will happen. So until this entire region, you don't have any switching. So this is the situation where you definitely get more and more fundamental, but you would lose the control over the harmonic. So this is called as the overmodulation region. So until MA is equal to 1, okay, MA is equal to 1, or rather, let me write it this way: 0 less than or equal to MA less than or equal to 1 is called as the linear region of operation. Okay, and once you have this one in this region, overmodulation, we know that the V control peak is greater than V triangle peak. That is a minimum requirement. We might have a situation that there is a huge region of V control where it is greater than V triangle. And as we go here and further and further, as we go further and further, you may be having larger and larger voltage, eventually reaching the square wave. Okay, if you have a triangle and the sign is always greater than that, there would be only very small amount of pulses in the beginning here. Okay, a few pulses, and then it is gone. So if you choose that slope of the triangle, there is this triangle this way, and if you choose the slope of the sign greater than the triangle and the magnitude is larger, then you are never going to have any pulses here. Okay, every time this would be going like this. Okay, this pulse is always faster, and therefore you will never get any pulse. So that is the situation where you get the square wave, and that is corresponding to about 27% increase in the fundamental voltage. So here it is corresponding to VDC. Here it is corresponding to 4/5 VDC. I have already normalized it with this one, so it is VDC 4/5 and 1 here. Okay, so the maximum boost I get would be 27% when you are operating at square wave, but we lose the control over the fundamental. Okay, so from MA greater than this one, we don't have any control over the harmonic. It may eliminate something because there are some pulses, but in general, I don't have any control over the harmonics. Okay, harmonics are not completely under our control. As we move further and further, it will be lower and lower. Now note that this region I have drawn it as small, corresponding to 23. It is not linear. So typically this MA would be greater than 5 and all. in this region. Okay, so you will get that it's going to be not linear, though the way I've drawn is like this. This is a larger scale here. Okay, so as we make more and more magnitude for the sine wave, you will get lesser and lesser pulses, and it will push towards the overmodulation all the way up to the square wave, eventually reaching the square. But we would try to use this to our advantage sometimes. Suppose you have a driver motor drive circuit or some circuit, and this DC link comes from a rectifier. Okay, this is coming from a rectifier, which is in turn coming from a 230 volt supply. Now it might so happen that due to some adjacent the point of common coupling, there is some voltage drop, there is a voltage sag somewhere, and that would result in, let us say, 190 volt or something instead of 230 volt. We can always utilize this over modulation to ensure that the fundamental is maintained here. So VO1, I can maintain it to be whatever it is. Let us say some 180 volt here. I wanted that to be, and you are using this one. So if the input voltage drops from 230 volt to 190, you can always do some arrangement, use it in the over modulation region, such that I can maintain the voltage as we desire. Okay, so it is always possible to use the modulation, over modulation, for momentary, fundamental correction. Okay, so I think we have crossed the time, so I will just state this problem. The remaining part of the problem is for the three-phase, and then we'll look at that thing. So let me state the single-phase problem, and then we'll stop the class for today. So in this particular example, what we have done is that we are looking at a single-phase DC to AC converter, where output is single-phase AC, and I want it near sinusoidal output. So we would have filter or something after the inverter to get a sinusoidal supply. This is typically what we use for the home inverters. Home inverters, when they say that sine inverter, that's precisely what they do. They will have a sine triangle compared PWM, and then the output of that voltage would be filtered, and that filtered voltage would be given as sinusoid voltage. Okay, so this has to supply a load. Now I have not specified what is a filter, but the load is rated for 230 volt 50 hertz AC. Now you can choose an H bridge inverter, and I want you to use the sine PWM. Now this is a standard design choice which they make, is that when for 230 hertz I want the output 50 hertz, I'll choose that MA 0.8 correspond to 230 volt 50 hertz. So this is our design choice which we made. It is not a necessity, but it will be like we have some more control over slight increase in the output voltage if there is a dip, etc., without losing the harmonic control. So as I said, if it is in the over modulation, you don't have a control over it will no longer be sinusoidal output. It will have some harmonics. If you have a modulation index limited to 0.8, we still have a margin for a boost in the voltage. It could be when it is if it is 1 modulation index 1 MA1, then you could have actually had more than 230 volts. So if there is an input voltage VDC is dipped due to any external reasons, we will still have a control over the output voltage. I can boost it a bit. Okay, so that is the idea which we use. So this is the design suggestion which is given here. Now I'll just show you the calculation quickly. So if we choose the H bridge, we know that the design specification is given as the output voltage RMS should be 230 volt, and it is near sinusoid, near sine. F1 is 50 hertz. So we would want the peak of the thing to be 230 volt into root 2. That'll be about 325.2 volt. And we know that MA times VDC is 325. And we know that MA we have chosen it to be, MA max is chosen to be 0.8. So VDC, we can compute it using this one. Okay, so it will be about 400 volt. If it was MA is equal to 1 was chosen for 230 volt, then 230 volt RMS, I would have had VDC as 326 volt or 325 point whatever that number. So roughly 326 would have been sufficient. But since you have chosen 0.8, we would get a little excess voltage for VDC. Now, we know that if you want asynchronous PWM, you can choose MF to be larger than 21. So you can choose the 2500 Hertz as the operating point. And if you want minimum separation, then it'll be MF is equal to Fs by F1. So this will ensure that the harmonic content is, the lowest harmonic content is somewhere around 9 or above. So maybe you will have some 7th harmonic, but that is acceptable if you have that kind of a situation. Now we will be using this as synchronous PWM and very low MF if you have very high power, because at higher power you would lose a lot of energy in the switching, and therefore you want to keep the switching lower, the frequency would be lower. Whereas in the home inverter, typically you will be using about 10 kilohertz or 20 kilohertz, etc. Okay, home inverters, that's the frequency we would use. It is sufficient to use 2500 if you have a good filter, but the filter size would be increased if you are having a lower frequency. So the higher frequency, you would lose energy because there will be more losses in the inverter, but the filter size can be reduced. So as a concluding last word, this is the idea. You have the fundamental, you have the harmonics, you choose the filter such that this would be completely eliminated. Okay, so let me stop with this one for today.